The main topic of Lab 4 is improper integrals. In general, the way you deal with improper integrals in SymPy is very similar to how you deal with just regular proper integrals. So in this example file, instead I will focus on dealing with a complicated type of functions that are defined through integrals. We'll start with adding our usual libraries. I will also add a new variable t here, and I will make it positive. This condition is there just to make creation of my function easier. However, you will see that I will be ignoring this condition throughout this file. For your problem file, while you do need to create variable t, you do not actually have to make it positive. So the function that we will be talking about in this video is called gamma functions. This is quite complicated function, but it appears in a lot of different places in mathematics. We define it to be gamma of t equals to an integral from 0 to infinity of x to the power t minus 1 times e to the negative x dx. And so notice t is my variable. If I plug in some t, it will go inside of this integral. Then we can integrate with respect to x. And if the integral is convergent, we have our value. So while I did define t to be positive, it doesn't have to be positive. It could be any value here. And as you will see later, I will use even negative values here as well. Another thing you should notice is that if t is the positive integer, then this is actually quite simple integral. You can use, for example, integration by parts to solve it. However, for non-positive integers, this is a more complicated integral. So how do we define it in SymPy? Well, there are two ways of doing it. The first one, kind of an easier way, we have an actual command that creates a gamma function. So sp.gamma, this creates my gamma function, and SymPy knows what that is. However, I will define it here using an integral first. So we'll create our inside, which is the integrand, that's x to the power t minus 1 times exponential of negative x. And then my g, which will be my gamma function, is the integral of that inside from 0 to infinity. So as you can see, SymPy recognizes that this is the same thing as gamma function. So now let's evaluate this function at a few points. So I will evaluate it at 4, at -0.5, and at -1. As you can see, gamma of 4 will equal to 6. Gamma of -0.5 equals to about -3.5 and so on. So you can see I can actually evaluate at negative values. And gamma of -1 is this symbol. It looks like zoo, but really what it says that it's undefined at -1. Okay, so next let's plot. So I will start in our normal way. I will lambdify my gamma function, and then I will try to plot it. But as you can see, I have no plot. In fact, I get an error. And the error is something about converting to Python scalars. It, in essence, cannot convert. The error happens at lambdify. So this command failed. It couldn't do lambdify. It couldn't convert into NumPy. So the reason for that is that our definition for gamma, which was through the integral, is too complicated. We need to do something else. And what we need to do is use vectorize to fix this. So I'm going to redo my picture. I will lambdify first, and then I will vectorize my answer. And then I will plot again. And as you can see, now it works. So here's my gamma function. So as you can see, at 0 we have a vertical asymptote, at -1 we have a vertical asymptote, at -2 we have a vertical asymptote, and then we have these U shapes everywhere else. One other things I should point out here is that since we have so many vertical asymptotes, Matplotlib may fail drawing a graph if you pick one of those points. So I had to be very careful here when I created my x values for graph. As you can see, one of my values is negative 2.51, and this is so that I don't ever hit precise integers here, negative 2 or negative 1 or 0. So next, let's look at a few interesting properties of gamma function. So consider the following sequence of numbers: gamma of 1, then gamma of 2, gamma of 3, gamma of 4, and so on. So it's a gamma of positive integers as a sequence. As you can see, we get the following values here. So gamma of 1 is 1, gamma of 2 is 1, gamma of 3 is 2, gamma of 4 is 6, and so on. So try to figure out what is the pattern here. For example, if I would take gamma of 8, what would be my next number? The second sequence is the following sequence. So it's gamma of 1/2 squared, and then it's 4 times gamma of 3/2 squared, and then 16 over 9 gamma of 5/2 squared, and so on. If I evaluate these three functions, I get the same answer, which is pi. So what should be my next um, command here that gives me pi as well? So try to think about it, and if you're ready, you can scroll down to the end of this file or scroll to the end of this video to see the answer. So now that we have defined the gamma function, we can do to it anything that we could do to any other function in SymPy. So we can integrate it, we can take derivative of it, we can evaluate anything. So for example, let's integrate gamma function between 1/2 and 2. And as you can see, we got some answer. So it works pretty well. Next, let's plot the graph of gamma function, and let's also shade the area represented by this integral. So here I want to introduce a new command, fill between. And this is how it works. So we define our figure. We have our x values. I will go from 0.001 till 3. So I don't want to start at 0 because remember the function is undefined at 0. So if I start at 0 here, it will try to evaluate it and it will fail. So it's easier to move it slightly. I will then plot my graph in blue, and then I want to fill the area between 1/2 and 2. So I will have to create a new sequence of x values that is represented by this integral, so from 1/2 to 2, and I will use plt.fillBetween. So then I have my x values from where to where and up to where, so up to my graph. So it will fill the area between x-axis and my graph. Alpha here is just opacity of the filling. Usually you don't want it to be too opaque, so you make it like 0.3, 0.4, that'll be good enough. And that's it. The rest is more or less the same. So here's my answer. That's my graph between more or less 0 and 3. And here's the shaded area between 1/2 and 2. So the shaded area is the area that equals to about 1.56. So now let's try to answer the questions about pattern. So I will start with the first pattern, 1, 1, 2, 6, 24, and so on. So this is a factorial. If you're not familiar with factorial function, it's in essence just a product of consecutive decreasing integers from the number you have until 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. And specifically for gamma function, gamma of t is just t minus 1 factorial. So for example, gamma of 5 will be 4 factorial, which is 4 times 3 times 2 times 1, so that would be 24. So now you can see all of these values are just that. So gamma of 5 factorial is 24. Gamma of 6 factorial will be 120, which is we have times 5. Then gamma of 7 will be 6 factorial, so it's 120 times 6, that's 620, and so on. So gamma of 8 will be 720 times 7, which is 7 factorial, and so on. So that's the first sequence. Now, you should notice that there is another way to write gamma function. Instead of writing it as a t minus 1 factorial, I can write it as t minus 1 times gamma of t minus 1. So for example, gamma of 5 can be written as 4 times gamma of 4, because this will be 4, and gamma of 4 will be 3 times 2 times 1. And this is a very nice recursive way of defining gamma function. And I will use this to see something about my second sequence. So let's look at the second sequence now. The point of a second sequence is, in essence, is to assume first that this pattern happens not just for integers, but for every number. So notice my first value is gamma of 1/2 squared, and that equals to pi. So if I solve this for gamma of 1/2, we know that gamma of 1/2 will be square root of pi. So now let's look at what should be gamma of 3/2. Well, gamma of 3/2 by this property should be 1/2, which is 3/2 minus 1, times gamma of 1/2. But gamma of 1/2 is root of pi, so this should be 1/2 times root of pi. If I square both sides, then gamma of 3/2 squared will be 1/4 times pi. So then move that 1/4 to the other side. I will have that 4 times gamma of 3/2 is exactly pi. And that's this part. Now we can repeat the same process, same thinking. What's gamma of 5/2? Well, that would be 3/2 times gamma of 3/2. We know what gamma of 3/2 already equal to. Plug in, you will have pi in it. Solve for that pi, and that's move everything else to the other side. And this will give you this number. So to find the next function, in essence, what you all you have to do is consider gamma of 7/2. So then gamma of 7/2 will be 5/2 times gamma of 5/2. Square both sides, move everything that isn't pi to the left, and you will have another function that equals to pi. So since this rule seems to work for any value of t, we sometimes call gamma function a generalized factorial function. In essence, it generalizes how factorials work for non-positive integers. So try to play around with this function and, for example, try to see what gamma of negative a half is. In fact, try to do this without using Jupyter, instead of using this property and the fact that gamma of positive 1/2 is root of pi. And then try to confirm your answer with Jupyter, see if you got it right. Lab 4 will have 3 problems. The first problem will deal with probability density function. You don't need to know the actual probabilities. Everything is given to you by the problem. Note that the last part of the first problem, where you have to deal with something called cumulative probability density function, you will have to create this more complicated type of a function, similar to what we discussed in this example file. Note, however, that the variable t there is part of a bound, not part of the integrand. So be careful when you define it. The second problem deals with a family of functions with which you need to plot and find some integrals. So you would have to remember how to create family of functions and how to plot multiple graphs on the same plot. Finally, the third problem is probably the simplest problem, and that's a problem that deals with a very specific function. You will have to find some integrals of it, and answer a few conceptual questions about that function.